Hello. In this video, we're going to finish up the example involving the wildebeest population. Recall we used a difference equation to get a nice simple model, but we needed to find the proportionality constant R. And since we have some data to work with, we're going to use that to help us estimate R. As you recall, the first step was to find the change for each group of years. So in other words, change is always the future minus the present. So the future population minus the present population means that in 1959, we were expecting a change of 51,000 wildebeest. And then we continue that on for the rest of the data points. And so if we want an estimate for R, then as you recall, it's just the ratio of that change divided by the current population. And so for this particular time period, that growth rate is 24%. And as we drag this down to get the other values, the good news is that they are all relatively close to each other, and they kind of bounce around. Some are smaller and some are bigger, but there's no obvious trend to these numbers. The bad news is they're not all the same. If they were all exactly the same, we would have a perfect model and we would be done. But since they're not, let's go ahead and pick the average and see what that does for an R value. So we're just going to take the average of all these. And see what we get. So we get about 0.24. So it's a bit of a coincidence that's the same number we got here, but that's what happened. So now we can do our model. Now remember, our model was a recursive relationship, and so P0 was 212, so we start there. And then remember, our model was the quantity 1 plus whatever our R value is, which we're going to use this for now, times the previous population. Now, it's very important. Make sure you use the same column when you're using the previous data value. If you come over here, that will confuse your model. And so notice we get 263, which not surprisingly is a great prediction, but we know it's not going to stay that great. Remember, in Excel, we have to put dollar signs around any cells that need to remain constant, and D12 is one of those, because when I drag this formula down, I don't want the D12 to change. And so sure enough, when I come down here, I have 1 plus D12 times E10, which is exactly what I want for my difference equation model. If we want to see what this looks like visually, we can highlight it using the control key to skip the numbers, the columns that we don't want. And so visually we get something that doesn't look too bad. All right, it's certainly not perfect, and if you look at it numerically, here we're more than 58,000 off. Here we're, 77,000 off. Sometimes we're a little low, like we are here. Sometimes we're high, like we were down there. Which is good that there isn't an obvious trend to the data, but it's still not perfect. If we want to do percent error, we can do that. We can just take the change, the difference between the two, so our model minus the actual, and then divide by the actual, and then we'll multiply it by 100 to get a percent. Of course, no error in our initial value. And overall, not too bad. Our worst error is 11%, which is higher than we would want, but some of them are still pretty close. And there are some are negative and some are positive. So overall, this is not a bad model. Now, what we might be interested in, though, is analyzing this model further. For instance, what happens if we try to interpolate or extrapolate? So we can do that. We can take this pattern of 75 to 77, and we can continue on until, say, 93. And then we can drag this down and also take that down to 1993. not the error, the prediction. Okay, and of course these are meaningless since we don't know the actual, since I haven't given it to you. And so as you can see, we have a prediction of about 81,95,000 for the wildebeest population in 1993. So that's about 8 million, 8.2 million. And if we want to go all the way to 2023, we can do that. And notice we're getting 206 million. That seems like a really big number. Without more investigation, might not be for sure that it's right or wrong, but it certainly seems suspicious to have that many wildebeest in the Serengeti. And sure enough, if you do some research, you'll find out that yes, in fact, this value is not accurate. That actually the wildebeest peaked at about 1.5 million, and in the 90s we're down to about 1 million again. So clearly this model is not great for extrapolation. What about interpolation? And for interpolation, let's say we want to do a year like 1974. Okay, so that's clearly between these two numbers. And now, our difference equation is not going to give us a value for 1974, but we can tweak it. So let's go back to our example here. All right, so here's our model. We had R was approximately 0.24. So we have P sub n plus 1 is 1.24 times P sub n. And as you'll recall, we could convert that into an exponential model if we so choose, like we did in the financial examples, where I raise this to the nth power and then multiply by P naught. Now, this still doesn't help because the n's are valid as we described here, and what I would really like is a new variable t, where t is the number of years since 1959. And if we do that, then this is going to be 2, 4, 6, and so forth. And notice the t is just double the n. So if I wanted to convert this formula into a function, p of t, then notice I just need to do 1.24, and then since the n is just the t divided by 2, I just replace it with t divided by 2, and now I have my model. All right, or if I wanted to be a little more careful, I could write this as 212 times 1.24 to the t over 2. So that also works. And then 1974 corresponds to P of 15. (15) divided by 2 would be 7.5. And that works out to 1,064,000 wildebeest. Now, if you're curious, you can look this up, and it turns out the actual, as far as we know, is 1,058. And so that's not so bad. Now, one thing we haven't talked about is this data. What's the error in this data? Presumably, this isn't perfect values, right? It certainly doesn't round to exactly a perfect 1,000 every time. So there's at least that much error in, but maybe even this last digit may not be accurate, or maybe a couple of these digits may not be accurate. That would help us get a feel for whether this model and what this error is acceptable or not, right? So that 11%, maybe they don't expect to be more than 10% within the actual population anyway. So if that was the case, then this model might look even better. On the other hand, if these are really accurate numbers, then we would have to judge accordingly. But overall, we probably have an okay model for interpolation, but not good at all for extrapolation. So there's something else going on. And so we need to think about long-term behavior anytime we do a modeling problem. And so in this particular model, the limit as n goes to infinity of P sub n is clearly infinite because it's an exponential model. And that's unrealistic. Now, we may not need our model to be true out to infinity, so we may be willing to accept an unrealistic model far in the future because we're only going to use it for a short amount of time. But on the other hand, this is also a little bit of an indication that something else is going on, and so maybe we need a new model. And so this is where we would use our modeling process, the cyclical nature of it, where we built our model, we analyzed the model a little bit, and we realized we have to go back to our assumptions. And so in this case, let's try a new assumption that doesn't lead to an exponential fit. And so our new assumption is going to be assume that population is also, so this is going to be an additional idea, is also controlled by something called a carrying capacity. So you may have heard this term before, but it's this idea that a habitat can only support so many of a certain organism or animal. So presumably the wildebeest couldn't grow forever in number in the Serengeti because they're going to run out of food and water. Disease is more likely to spread if they're all crowded together. And so there's some sort of carrying capacity. And so the idea is that as the wildebeest population gets closer and closer to that number, then some of those hindrances are going to start to have more of an impact, and so their population will change accordingly. But how do we express that mathematically? So mathematically, we're going to still keep with our difference equation idea, and we're still going to assume the proportionality is there with the current population, but we're going to add another term. And so you might think about what term would incorporate a carrying capacity, which let me go ahead and give the name M. And it turns out that one possibility is to do the difference of M minus P sub n. And this goes back to Verhulst in the 1830s. So it's not a new idea, but it works pretty good in some situations. And one of your exercises will be to see how it works for the wildebeest. But the idea is this, is that if M is really large and P sub n is really small, then this is going to be a large number, and so there will be more growth. Now, if P n is too small, well, then this will be a small number, and so that'll be balanced out. But notice, as P sub n gets closer to M, this gets to be a smaller and smaller number, which means my change is going to get smaller and smaller. And so this has the nice feature that when P sub n is small, or 0, we're going to have no growth. And if P sub n is close to the carrying capacity, I'm going to have no growth. And if I'm close to that, I'm going to have limited growth. But here in the middle, here at M over 2, I'll have the most growth. So this is the idea, is that I'll have a lot of growth when I'm not far from, or when I'm far from the carrying capacity and also far from very few of the animal in question. So what does this mean for long-term behavior? Under this new assumption, if I take the limit as n goes to infinity, we'll see that the carrying capacity will be the limit. Now, while we're on the topic of long-term behavior, we can ask ourselves, is this a stable or unstable equilibrium? All right, and so notice that M is an equilibrium because as I get closer to M, this model is going to predict that the population will just continue to stay close to the carrying capacity. And it turns out in this case, this is a stable equilibrium because even if my population changed a little bit, let's say I dumped some more wildebeest in or I took a few out, it's still going to stay around M wildebeest if the model is true. An example of an unstable equilibrium would be 0. So notice 0 is an equilibrium in the sense that if I start with zero wildebeest, I keep 0 wildebeest indefinitely. But notice all I have to do is add a few extra wildebeest, and then presumably, if this model is true, they'll grow and grow and grow, and we'll never get back to 0. And of course, we can't have negative wildebeest, so we can only add, we can't subtract. But in this first case, we could add or subtract, and the model predicts it will come back to M. So this is a little bit of a glimpse into looking at long-term behavior and some questions we can ask ourselves. So it may be that we don't care so much about the population getting it completely right. What we may care more about is what is the long-term prediction. And if the long-term prediction is a number that is higher or lower than we were wanting or hoping or expecting, then that can be useful information, even if we don't get all the data values along the way perfectly right. So we'll play around with these ideas more in future sections, but for now, let's do another example back to the medication idea, and we'll do that in the next video. So we'll see you there.